So let me start. I've known Dave for a long time, but the thing I remember is that I sticks in my mind that he is perhaps famous for is this idea, which I believe I have correct, of drilling a hole to the center of the earth, which I have paraphrased somewhat, like Jules Verne, and trying to see what it would be like to go, dig a hole that's way beyond the mobile discontinuity, down to the center. I don't know how far, but I just thought it was an extraordinarily off-the-wall idea, and he will talk about that. But if he doesn't talk about it, you at least heard about it. So our next speaker is Dave Stevenson.
I don't want to drill, I want to make a crack. And Jules Verne, damn it, they only went down 20 miles. So much for Journey to the Center of the Earth. Okay, now, of course, there's a little bit of overlap with previous talk. Same introductory comments, magnetic fields are ubiquitous. They come primarily from currents. Permanent magnetism, of course, is the way that we look at previous magnetic fields. So in the context of this talk, it's the memory of previous dynamos. And in order for this to work, you need cold magnetic minerals, and that's not available everywhere. And of course, we're assuming that there are no monopoles. So here's my outline. I'm going to make some generalizations from the observations, and then I'm going to talk about the mechanism that we believe is responsible for magnetic fields in planets and indeed in the sun and probably in the galaxy, which is the dynamo process. I'm going to focus on the idea that cooling is the centrally important thing to think about. That the reason why you can have the convection that drives a magnetic field is cooling of the core. And once you appreciate that idea, you can appreciate why it might not always work, because it's not guaranteed that planetary cores will cool. I'm going to talk about the fact that low thermal and electrical conductivity are desirable. I know that's counterintuitive. Normally you would say, oh, I need a good electrical conductor. I'm going to argue the opposite. I'm going to argue that you need a poor electrical conductor. Of course, you can't do it with an insulator, but a poor electrical conductor is better than a good electrical conductor. Why? Because whenever you have high electrical conductivity, I'm talking about condensed matter like liquid iron, whenever you have high electrical conductivity, you also have high thermal conductivity. And when you have high thermal conductivity, that inhibits convection because the heat can be carried out by conduction. I'm going to argue for the unimportance of rotation, though it's admittedly true that we don't fully understand the role of planetary rotation. And I'm going to talk about some general principles that govern the geometries, stabilities, magnitude of the observed fields. So first, to summarize what you saw in the first talk, we see in our solar system, among the planets and satellites, 4 categories of fields. We see some bodies that have large fields, predominantly dipolar. For me, large means of order of Gauss, very crudely speaking. And those bodies are Earth, Ganymede, Jupiter, Saturn, and Mercury. Mercury somewhat smaller, of course, in magnitude. We also see 2 bodies that are really, I would argue, distinctively different. And they're predominantly non-dipolar, Uranus and Neptune. We also see fields that are expressed in the crustal magnetism and are evidence for past dynamos, Moon, Mars, some asteroids. Who knows about Venus? Venus actually, it's interesting, it's a close call. The surface temperature of Venus is actually below the Curie point of likely magnetic minerals. However, if you have something sitting at 700 Kelvin for billions of years, it will tend to lose any previous magnetization. And so I would not exclude with certainty that there's permanent magnetism on Venus, but it is unlikely. You could also get fields from induction, and that's what you get in the case of Europa and Callisto and perhaps Io. These are fields that arise because you have a body with a conductor in it, and it's sitting in a magnetic field, and the magnetic field is changing, and this induces eddy currents with their associated magnetic field. And that, of course, is the way we decided that there are water oceans in those bodies. And in the case of Io and Krishnan's work, possibility of a magma ocean. So here's a summary tabulation of those large global fields that are predominantly dipolar. And just to remind you of something that I think is rather interesting, Earth and Jupiter are actually kind of similar in these attributes. And it is striking that when you take the spectrum of Earth and the spectrum of Jupiter, they look kind of similar. By spectrum, I mean spherical harmonics. Similar dipole tilt, similar ratio quadrupole to dipole, evaluated at the core, which is what you should do, of course. And to me, this is striking because Earth and Jupiter really are very different as planets. Very different structure, very different materials, very different luminosities, almost everything you can think of, except the magnetic field. They're remarkably similar. And that's, on the one hand, a suggestion of some kind of generalization that you might make on dynamos, but on the other hand, somewhat disturbing because you would like to think you could use magnetic fields to learn about internal structure. So I would have to say this is a puzzle. Saturn, like Mercury, of course, has small dipole tilt. And that, too, is telling us something interesting that we do not understand very well. And then Uranus and Neptune, which are somewhat similar to each other, large dipole tilt, similar amount of quadrupole and dipole. And here is a portrait gallery of Earth, Jupiter, Saturn, Uranus, and Neptune. And here you see the various field geometries. There's no particular preference of the direction of the dipole, nor should there be, of course, because fundamental physics says that there's nothing special about the direction of dipole and the direction of rotation axis. There's nothing in the physics that would prefer one over the other, assuming that there are no other fields around. Variety of tilts. This blue line is the equatorial plane. Uranus, of course, is tipped over on its side, but the large dipole tilt is evident in both cases, and in the case of Uranus and Neptune. And so you see a diversity there. And let's now turn to some general guiding principles. So we think that large fields come from dynamos. And dynamos come from fluid motions in the presence of a pre-existing magnetic field. And those motions must be in an electrical conductor. In the next slide, I will give you some numbers for that. The convection can arise through a compositional buoyancy. That is the presence of material less or more dense than the other materials in the system, or thermal buoyancy. That is, as a consequence of the desire of the planet to get rid of heat. So we think that convection dominates. Now, in the dynamo literature, there are a huge number of papers that talk about other ways of making dynamos. It's important for you to understand that although there are other ways of making dynamos, as a group, the alternatives are much less efficient. People like to use waves. They like to use other kinds of motions. But one of the important things we have learned about in dynamo theory through people like Fritz Busse is that you need large-scale vertical motions, Otherwise, you're not going to get much of an external field. Very important result that he derived. And that suggests convection. Now, the interesting thing about the dynamo game is that when you look at the theory of it, what you find is that for terrestrial planets, including Earth, it's difficult to run a dynamo. And the reason why it's difficult is because the heat that comes out of the core can be mostly carried by conduction. If you have a good electrical conductor, it will be a good thermal conductor. And if it's a good thermal conductor, the heat can escape by conduction. So that is the central message I want to get across for terrestrial planets, that dynamos are difficult because the energy budget for sustaining convection is often marginal. And related to that, high electrical conductivity is a disadvantage. And that, of course, comes from a fundamental rule in condensed matter physics called the Wiedemann-Franz relationship, which says that the thermal and electrical conductivities are in a proportional relationship. And the reason, of course, is that electrons are responsible for carrying the electrical current, but also responsible for carrying the heat. That's why metals are good thermal conductors. So let's talk for a moment about the basic principles of a dynamo. And I show over here on the right a mechanical analog. Of course, planets don't look like this, but the principles expressed in this disk dynamo have one-to-one correspondence with various aspects of generating a magnetic field in a planet or indeed the sun. So what do you have here? You have a shaft, you have a spinning disk, and this disk is metallic, it's a good conductor, and the system is threaded by a magnetic field. So from Faraday's law, the motion of this disk induces an EMF between the shaft B and this contact, sliding contact A, and that EMF will drive a current through this circuit. And because the wire is threaded in the particular sense, the right-hand sense shown here, we have from Ampere's law the expectation that this current will induce a magnetic field which is in the same sense as the one that produced the current. So this is a bootstrap, and the bootstrap will work provided you do work. That is, you keep the disk spinning. So you have to do work. There's no free lunch. You have to do work, and the work that is done in moving this through the magnetic field offsets the dissipation, the heat that is produced by the electrical current through the wire. Now pause for a moment and think about the attributes of this system. A crucial attribute is differential motion, the fact that this piece is moving relative to the rest. If I made the whole thing rigid and just spun the whole thing, I would not generate a magnetic field. So differential motion is crucial, and in a planet that comes from fluid motion. An electrical conductor is crucial because that's how you get a current flowing. And an interesting and tricky aspect of this is the topology. You'll notice that if I wrapped the wire the other way, it wouldn't work. I would actually get what's called an antidynamo. It would destroy the previous field, and antidynamos exist. So planets have managed to break symmetry in the fluid motions by producing a kind of motion that enables dynamo generation. It is also true, by the way, that dynamos are intrinsically three-dimensional and symmetry breaking. You must have at least three spatial dimensions. If we lived in a two-dimensional universe, there would be no magnetic field generation. The differential equation that describes in a fluid the same physics as this mechanical model is shown here. It's the induction equation, a deceptively simple equation in which V is the fluid motions relative to rigid rotation. Rigid rotation doesn't do anything for you. This is the diffusion term, and the diffusivity here is 1 over mu naught sigma, where sigma is the electrical conductivity. So just by dimensional analysis, looking at this equation tells you that the fluid motion is important. That is, you can use this term over here to offset diffusion, which will always tend to reduce the field. Fluid motions are important provided this particular dimensionless number is large enough, and this number is called the magnetic Reynolds number. So if you have a fluid flow in which the magnetic Reynolds number is greater than of order 10, then perhaps you can have a dynamo. The perhaps is important because this particular topology is not guaranteed in all fluid motions. Turns out, for example, that if you have fluid motion with zero rotation, Rayleigh-Bernard convection, for example, it will not generate a magnetic field. It doesn't have a sufficient complexity to it. And this is perhaps one of the puzzles in dynamo theory and one of the missing links in our understanding. Everybody understands this as a necessary condition for a dynamo, but it's not a sufficient condition. So what is usually needed for a planetary dynamo is a fluid conducting region in differential motion. The dynamo region does not have to be the core, but usually the outer regions are usually insulating. There is a counterexample in exoplanets, of course, and that's hot Jupiters. I don't propose to talk about hot Jupiters here. Doubtless will come up later in the workshop, but there are a lot of interesting questions there about where the field, or what field there is in hot Jupiters and where it's generated. But it seems that convection is the likely source of the necessary vertical motions, and the driver for the convection is usually cooling. Now, this is really important. Cores of planets, and I don't care whether it's terrestrial planets, giant planets, whatever, do not have large intrinsic heat sources. By intrinsic, I mean radioactivity. So the heat that comes out of Earth is in substantial part, we think roughly 1/2, due to radioactive decay. But it's important to understand those elements are not in the core. So in the case of the Earth, which is the example we understand best, the reason why there's a heat flow that comes out of the core is because the core is cooling. The core is cooling because the mantle lets it cool. So in the case of the Earth and in terrestrial planets in general, the mantle is the master, the core is the slave. And if the mantle says, I don't want to cool, the dynamo will die. So it's absolutely crucial to understand the planet in totality, including the atmosphere, if there is a thick one, for this question. So cores usually have no intrinsic heat sources. The cooling can, of course, provide thermal buoyancy. That's ordinary thermal convection. Cooling can also promote phase transitions. So if you have insolubility, or if you have the growth of an inner core that is compositionally different from the outer core, as in the case of the Earth, you get compositional buoyancy. But the driver is cooling. It is always cooling. Don't make the mistake of thinking, the reason why the Earth has a magnetic field is because of the inner core. You will see that statement made. The crucial reason why the Earth has a magnetic field is because it's cooling. If it didn't cool, the growth of the inner core would stop, the magnetic field would stop being generated. So let's talk about the terrestrial example. And here, by the way, is a numerical simulation, an old one, Gary Glatzmeyer and Paul Roberts, classic work back in the 90s. You can see this very complicated spaghetti. I'm not giving here a talk about the intricacies of dynamo theory. That's a very complicated subject, but suffice to say this is a supercomputer calculation, and it's a hard one. And there's some reason to suspect that people are still not doing it right. That is, they're far removed from the correct parameters for the real system. But it does, in some cases, give a field similar to what we see. So the way it works in the case of the Earth, for example, is you do some model of thermal evolution. I've done these, Jerry Schubert, many other people have done these models. And that model says, the radioactivity in the mantle is declining, therefore the mantle is cooling, and because the mantle is cooling, the core will also cool. So the mantle is the master, core is the slave. The core is cooling, heat flows out of the core. If the amount of heat that flows out of Earth's core is more than can be carried by conduction alone, you will get convection, and then you grind through the numbers to get an estimate for convective velocities. And mixing length theory, the same theory that people would use for the outer convective zone of the sun, will give you velocities like 10 to the minus 4, 10 to the minus 3 meters per second. There's a large uncertainty in this game, but these are typical numbers for a core convective heat flow of 10 milliwatts per square meter. The total heat flow through the Earth's surface is 80. in these units. For liquid iron, the magnetic diffusivity is about 1 meter squared per second. Length scale, the size of the core, about 10 to the 6 meters. And so the magnetic Reynolds number, the crucial dimensionless number, is 100 or even 1,000. Notice an important point. This is comfortably in excess of what we think is needed to drive a dynamo. And so you might look at this and say, oh, no problem. The UF has no difficulty at all. But I assure you that is the incorrect conclusion. Why? Because this number up here, this heat flow and this convective velocity, can plummet to 0 with just a small change, like say 50%, in your choice of thermal conductivity. Because if I increase the thermal conductivity, the heat that's carried out by conduction will be all of the heat. You will have no heat carried by convection, and this number will plummet to 0, and this will plummet to 0, and the magnetic Reynolds number will plummet to 0. So the UF is actually precarious, we think. Now, a comment about rotation, the Rossby number, which is a measure of the effect of rotation, small Rossby number means large rotation, is actually very much less than 1, and that's true even for Venus, which of course raises the puzzle of why Venus has no magnetic field. And I would argue that the reason why Venus has no magnetic field is because the core is not convecting. It has nothing to do with Venus's slow rotation. So the central issue then with cooling is whether the heat flow exceeds conduction along the adiabat in the case of a homogeneous body. And if the thermal conductivity is high, then it's hard to satisfy this criterion. I will tell you that our current understanding of the Earth is that we have a crisis because the thermal conductivity is higher than we previously thought based on quantum mechanical calculations. Heat flow by conduction alone out of the core for the Earth is about 15 terawatts. Heat flow through the Earth's surface is 44 terawatts. The 44, of course, is a measurement. The 15 is a calculation. You might say, okay, 15 is less than 44. What's the problem? The problem, of course, is that most of this 44 should come from the mantle. And if you do have this 15, how are you going to keep that going through geologic time? Plate tectonics matters. It's entirely likely that the reason why we have a dynamo on Earth is because of plate tectonics. Why? Because plate tectonics allows the Earth to cool efficiently. Now, of course, in a heterogeneous body, there are other issues: inner core growth, snow, rain, whatever, weather. And if you have inadequate cooling, you can turn off a dynamo. This is a central problem for terrestrial planets. It's not really that important for gas and ice giants. When you do the calculation for those bodies, you find that you're in a more comfortable regime. You can tolerate a bigger change in heat flow. Don't worry, Jupiter's dynamo is not going to turn off. Earth's could. Question of rotation, just to clarify this, dynamo action requires that the characteristic timescale for fluid motions is small compared to the magnetic diffusion time. Magnetic diffusion time is like so, 3,000 years roughly for the Earth. That's the time that the Earth's magnetic field would decay away if you suddenly turned off the dynamo. But the point is that these motions are slow compared to rotation timescales, even for Venus. And so rotation matters, and we think that rotation plays a crucial role in breaking the symmetry of the motions and thereby allowing for the dynamo action. So all planets are fast rotators from the perspective of dynamo theory, including Venus. Venus has a rotation period 243 days. That's really fast compared to this time scale. And so we think that the core of Venus, if it's liquid and if it's convecting, it should drive a dynamo. The fact that it doesn't drive a dynamo is because it's not convecting. The reason why it's not convecting is because Venus is not cooling efficiently. It may even be heating up at present. And that in turn may be related to the fact that it has no plate tectonics. This is speculation. So, now a disturbing fact that we don't actually know the criterion for a planetary dynamo. This is astounding. If you go look at the literature, you see thousands of papers about dynamos. And it will not be apparent from reading those papers that the fundamental question is unanswered. But it's true. The fundamental question is unanswered. We do not know exactly what the criterion is for a planetary dynamo. That is, if somebody gives you a planet, gives you precise information on composition, precise information on evolution, precise information on heat flow, blah, 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 I can't tell you for certain whether or not it will have a magnetic field. I suspect, many of us suspect, that it's close to the criterion for convection, which is an easier thing to calculate. We don't know this for sure, but the suspicion is that once you reach that criterion for convection, you only have to go slightly beyond it, and already from mixing length theory, where the convective velocity goes as a cube root, the velocity climbs rather quickly, and the magnetic Reynolds number becomes large enough. This is, however, a difficult problem, and we are not yet at the position of solving it. What determines the field geometry and stability? We don't know that either. The sun, of course, is an AC dynamo. That is, the sun does this, has a solar cycle, 11 years, 22 years total. The Earth has a square wave, sort of like this, and then it goes through reversal. It's a different kind of time behavior. The sun has a reversing magnetic field with a time scale that we think is a characteristic dynamical time scale. The time scale for reversals on the Earth is not related to the convective time scale. It's hugely larger. And we think that reversals come about through the large fluctuations in the background convective motion. We can make a list of the things that matter: the thickness of the convective layer, the presence of shearing motions, location of buoyancy, nature of boundary conditions, blah, blah, blah. And this issue is affected by the same things, but this is not well understood. Finally, the question of the amplitude of the field. People always ask this, why does the Earth have 1 Gauss? Why does Jupiter have 4 Gauss? Why does Mercury have 100 times less? The most obvious comment to make about field magnitude is that even if you thought you had a theory for this, you could be pretty damn sure that it has huge variance. Because if you look around our solar system, you see remarkable diversity. I've already talked about this. Jupiter and Saturn differ. Mercury is surprisingly small field. Paleolunar field, surprisingly large. Surprising. That means that there's something here we don't understand well. What I can tell you is that there are 2 different ideas for what determine the field magnitude. And they both sort of work, but they're actually kind of different, and they have different implications. So one of them is force balance. You look at the equation of motion, you notice that there are 2 important terms, the Coriolis term and the Lorentz force. You balance them, this gives you an Elsasser number of order unity. This is the Elsasser number. B is magnetic field, sigma electrical conductivity, rho fluid density, omega rotation rate. So you notice this is a criterion that depends on the conductivity and depends on rotation. Our planets moderately satisfy it for the surface field. There's an energy scaling, which looks superficially attractive. The argument behind this is actually much more complicated, but essentially if you take the usual measure of magnetic field energy density and match it with the kinetic energy density, you get something that roughly works. This is the work of Christensen. The velocity you put in here comes from mixing length theory, so you'll notice this one predicts a field that depends on heat flux, does not depend on electrical conductivity, does not depend on rotation rate, and yet it does roughly about as well. The evidence supports energy scaling, I would say. Uli has managed to show that he can put the planets and some stars on the same diagram, and this sort of works. So to conclude, dynamos are easy in giant planets, I think. Dynamos are difficult in terrestrial planets. It's easy to create conditions in which it will turn off. Cooling is crucial. Diversity is more striking than universality. That's a comment Steve made. We still lack a predictive theory. We need more numerical work. I can talk at length about the enormous difficulties of doing this. There are also people who do lab simulations, sort of like giant washing machines. Mineral physics helps. It turns out mineral physics is driving a lot of our thinking about the materials, the phases and so forth. And of course, as always, future phase space missions and exoplanet observations. And I will stop there. Thank you.